In the last video, we looked at the precise definition of the limit of a sequence, and it has all these epsilons and deltas. But what we saw is that we can use all of our old limit laws and limit techniques to evaluate limits if we can find a function f of x that gives us the values of the terms in the sequence. Now, let me just quickly remind you of a couple of things that we can say about limits. If the limit as n goes to infinity of an does not exist, we would say that the sequence diverges. So if we're not really approaching anything at all, what we would say is that the sequence diverges, it doesn't have a limit. And if the limit as n goes to infinity of an is infinity, meaning we're not really approaching a number, but the terms grow without bound, then we would say that the sequence diverges to infinity. So in both cases, we would say that the limit diverges, but if we can say a little bit more specific, provide more specifics about why it diverges because the terms grow without bound, then we can add this explanation, the sequence diverges to infinity. All right, so let's look at some examples of sequences and determine whether they converge or diverge. All right, let's start by looking at the sequence. Let's look at the sequence an equals 2 to the n. All right, so we want to take the limit as n goes to infinity of 2 to the n. And what we argued previously is that we can think about this just as a regular limit, where we have the limit as x goes to infinity, and x is a continuous variable. And we want to know what that approaches. And if you know what the graph of 2 to the x looks like, we can therefore determine the limit. It turns out that 2 to the x, if you plug in your graphing calculator, or maybe you just know what it looks like, it looks a lot like e to the x. It grows exponentially. And you can see that as x goes to infinity, the y values are getting larger and larger, which means we would say this limit is infinity, or the sequence diverges to infinity. Okay? All right, so there's one sequence. Let's look at another one. Suppose that an is not equal to 2 to the n, but it's rather equal to 1 over 2 to the n. What does that sequence approach? Well, again, what we can do is we can write this as a function in terms of x instead of n. All right, so we're going to take a limit as x goes to infinity of 1 over 2 to the x, or we can also think of that as a limit as x goes to infinity of 2 to the negative x. And notice that's the exact same function as before, except we've replaced x with negative x, which means its graph is going to look like the same function. Oops, let's make it a little better there. It never actually goes below the axis, and it's going to approach an asymptote just on the opposite side. So before we had y was approaching infinity because x was going to positive infinity. Here, 2 to the negative x is the same graph, just flipped horizontally, and it looks like the y values are approaching 0. So in this case, we would say, yes, this sequence does have a limit. Its limit is 0. Okay? Now, these are both examples of a very important type of sequence called the geometric sequence. And so let's actually look at that more general case. an equals r to the n. So r here is going to be some number. In the first case, we had 2 raised to the n, so r was equal to 2. In the second case, you can actually show that that's just 1/2 raised to the n, so r was equal to 1/2. But in the general case, what you can show is that the limit as n goes to infinity of an is equal to the following. Well, if r is a number bigger than 1, then we have a scenario like the first one. It's going to have exponential growth, and so we would say that the limit is infinity, it diverges to infinity. So that's if r is greater than 1. If r is less than 1, but greater than or equal to 0, then you have a number, a fraction like 1/2 that's being multiplied by itself over and over and over again. And you can see that as you raise it to higher and higher powers, the number gets smaller and smaller and smaller, and it's going to approach 0. And then we have one more case to think about, and that is r equals 1. And when r equals 1, notice you have just 1 to the n. Well, what happens when you raise 1 to larger and larger powers? Well, nothing, right? 1 doesn't change. And so in that case, we'd say the limit is equal to 1. All right, so here we've covered all of the cases where r is greater than 0. And notice if r is equal to 0, we can include that with the previous case. 0 to the n is equal to 0 all the time. So obviously the limit of 0, 0, 0, 0, that sequence has got to approach 0 as well. Now, you can also ask the question about negative values of r, but that's going to take a little bit more work. All right, so let's continue on. Let's look at another limit. Let's look at the limit as n goes to infinity of 2 over n plus 3 over 2 to the n. Okay? Now, if this was a regular limit with x, which is a continuous value, then what we would do here is we would break this up into more manageable chunks. And since we know that the limit of a function f of x and the limit of n actually are going to be the same, we can do that. Limit as x goes to infinity of 2 over x plus 3 over 2 to the x. And then with continuous limits, we have all these limit laws that allows us to chop up limits. And so we can actually write this as 2 times the limit as x goes to infinity of 1 over x plus 3 times the limit as x goes to infinity of 1 over 2x. And we've actually already looked at that second limit. We know that one's going to be 0. And then 1 over x, that's a pretty easy limit. As you take larger and larger numbers in the denominator, the fraction gets smaller and smaller. And so that goes to 0. And so we would just get 2 times 0 plus 3 times 0, so 0. All right, so we can apply our limit laws to these sorts of limits to break them down into simpler components, which is a very convenient thing to be able to do. All right, let's look at a harder problem. Let's look at the limit as n goes to infinity of negative 1/2 to the n. All right, now this is a little bit trickier. Let's actually write down the terms in this sequence so we can get a handle on what's going on here. So let's look at some of the first few terms, a0, a1, a2, a3, and so on. All right, so if I take negative 1/2 and raise it to the 0 power, that's going to give me a0, and anything raised to the 0 power, or any number, is going to be just 1. All right, so now a1, I need to raise negative 1/2 to the 1 power, which is just going to give me negative 1/2. And then when I plug in n equals 2, now I'm going to have negative 1/2 squared. So we'll get a value of 1/4. And then a3 would be negative 1/8. And maybe you see where this is going. It looks like the terms are alternating signs. They go from positive to negative, back to positive again. And then the denominator is growing by a factor of 2. Okay? Now, the challenge is that this function does not really work well for real values. If you plug in x equals, or n equals 1/2 here, which, well, if you write this as limit as x goes to infinity of negative 1/2 to the x, then that's not going to work because, well, if x is, say, a half power, then we're talking about square roots of negative numbers. And so this thing does not exist. So that theorem that we talked about earlier, saying that we could just think of this as a continuous function, isn't going to help us here. But the good news is there are other theorems that are useful here. And in fact, there is a squeeze theorem that can be applied to limits of sequences as well. And it says the following, that if an is less than or equal to bn and greater than or equal to cn, and the limit as n goes to infinity of cn equals the limit as n goes to infinity of bn, and that's equal to some number L, then the limit of an, the one in the middle, must be the same thing. In other words, if you have one sequence whose terms are always bigger than the sequence you're interested in, and another sequence whose terms are always smaller, and both the bigger one and the smaller one approach the same value, then we conclude that the one in the middle has nowhere else to go. It's squeezed in between the other two, and therefore its limit must exist. All right, let's scroll that up just so you can see that a little better. And so we'll see how that can help us for this particular problem. In fact, let's draw ourselves a little graph. So I'm going to use an n-axis here. This is going to be the index of the term. And so I could even draw some little dots here for my terms in the sequence. So at n equals 0, we had a value of 1. So I'll put a little dot there. At n equals 1, we had negative 1/2. So we'll put a little dot there. The next term, a2, was 1/4. And so that one's a little closer to 0. And then we'll see we're going to get back and forth, alternating between positive and negative, but always getting closer and closer to what looks like 0. But we don't want to just say that and claim it without justification. So how can we prove it? Well, here's the claim. an is less than or equal to 1 over 2 to the n. Because notice that 1 over 2 to the n would have the exact same terms in the sequence, but they would all be positive, right? So let me just add a different color here. If I were to graph out 1 over 2 to the n, it would look like that. Be 1/2. Then this one would be the same. This one would be a little smaller. And you'd see that for every single term, 1 over 2 to the n is going to produce a larger value, or at least as large as an. Similarly, we could also look at, say, negative 1 over 2 to the n. So the same sequence with terms that all have a negative sign, and you'd see that these ones are always going to be smaller. And so clearly, an is squeezed in between those two different sequences. And so what the squeeze theorem tells us is that if we can evaluate both of those limits, and they happen to be the same thing, then, well, we can conclude that an must approach that as well. Well, the good news is we've already actually evaluated those limits. The limit as n goes to infinity of 1 over 2 to the n was 0. We showed that a little bit earlier on. And similarly, the limit as n goes to infinity of negative 1 over 2 to the n is, well, it's just the same sequence with just each term negative. So it's got to approach 0 as well. And so that means that the limit of the sequence that's trapped in between, that's squeezed, must be 0 as well. There's nowhere else to go. And so this alternating sequence, 1, negative 1, 1/4, negative 1/8, has to approach 0 as well. So we can use the squeeze theorem. We can use that to compare sequences to figure out their limits. And in fact, this result is going to allow us, or this method is going to allow us to generalize our geometric sequence that we talked about a little earlier. So let me scroll up just a bit. We said that if you have r to the n, it's going to approach infinity when r is greater than 1, 0 when r is between 0 and 1, and exactly 1 when r is equal to 1. Well, we can extend that to include a couple of other cases. What if r is less than negative 1? So r could be negative 2, negative 10. Well, notice there, that is taking negative numbers that are large and multiplying them by themselves over and over again. And you can easily see that those numbers are going to get, well, bigger and bigger in absolute value. So if you take negative 2, multiply by itself, it goes to 4, which goes to negative 8 to negative 16. That's not approaching anything. That's oscillating back and forth between larger and larger numbers. And so we would say this one just does not exist, diverges. And then we could also look at the values of r between 0, let's make that a negative 1 and 0. And in that case, it will be much like the example that we just worked on, negative 1/2 to the n, where we show that it actually is equal to 0. So the limit will exist for all of those values between negative 1 and 0, as well as between 0 and 1. All right, so there's only one number we haven't taken into account, and that is r equals negative 1. And so let's think about that one for just a moment. If an is equal to negative 1 to the n, so r is equal to negative 1, what does that sequence look like? Well, when I plug in n equals 0, I get an equals a0 is equal to negative 1 to the 0, so that's 1. A 1 would be negative 1 raised to the 1 power, so that's negative 1. A 2 would be negative 1 squared, which is back to positive 1. And that pattern is just going to continue. It's going to go 1, negative 1, 1, negative 1, 1, negative 1. Well, is that approaching any particular value? Is there some target we could draw around some number and guarantee that our terms in the sequence will become arbitrarily close to that number? Well, it's not getting closer to 1, right? Because it's always going back to negative 1. It's also not getting close to negative 1 because the sequence keeps hitting 1 over and over and over again. And so we can rule both of those out. And in fact, you could make that same argument and rule out anything else. So in general, the geometric sequence has really 5 different cases. When r is less than or equal to negative 1, so here I'm including the one that we just looked at, we'd say that the limit does not exist. It just oscillates back and forth between positive and negative values without approaching anything. If r is between negative 1 and 0, the limit is 0. If r is greater than 1, it diverges to infinity. If r is between 0 and 1, including 0, it again approaches 0. And lastly, if r is equal to 1, well, it's a pretty boring sequence that just spits out 1, 1, 1, 1, 1, and the limit is 1. All right, so those are some examples of actually evaluating sequences with limits, or finding the limits of sequences, rather. And that's probably the most important thing to know how to do when it comes to sequences, is actually apply all of those old limit techniques that you learned in your calculus classes to actually finding the limit of sequences.